Hi everyone, welcome to GoClasses. In this session, we will solve all the GATE PYQs, all the GATE questions from this topic relations in the discrete mathematics. I am Deepak Poonia. I have done my masters from Indian Institute of Science, IISc Bangalore, and many times I have secured All India rank, top All India rank in the GATE Computer Science, like All India rank 53, All India rank 67, 206, etc. Now, also, let me tell you that discrete mathematics complete course is freely available for all the students on the GoClasses website. Okay, so just go to GoClasses website and there you will find the discrete mathematics complete course. Remember, complete course, all the lectures, all the concepts, all the homework, weekly quizzes, everything. So discrete mathematics complete course you can study from the GoClasses, the best course without any rote learning. You can understand every concept with proof. So let's start. So what are the type of questions that come from this topic? This topic is relations. From this topic, what are the type of questions that come? So the first type of questions that will come in this topic, that is finding types of relations, like whether the relation is reflexive, symmetric, antisymmetric, asymmetric, transitive, equivalence relation, okay, partial order relation. So this is basically finding types of relation. This is one type of question. Now let's see this type of questions. Let's see. So let's solve this question first. Before we solve this question, let me tell you that don't watch this video like a movie. I am solving these questions. You can also solve these questions. Okay. So just take your copy pen and solve these questions with me. I am solving, you also solve. So let's see this question. This is GATE Computer Science 1994 question, and the question is asking which properties, reflexivity, symmetry, antisymmetry, transitivity, which of these properties are satisfied by this relation. A relation is given to you, and let's look at the relation. What the relation is saying. Let's look at the relation. So this relation that is given to you, this is set of ordered pairs. This is set of ordered pairs. You have x comma y. This x comma y belongs to n square such that x is not equal to y. Okay, this is your relation. First of all, you tell me what are the base set of this relation. This relation is defined on which set? This is very important thing. You should find it out. I am asking what is the base set. This relation you have defined on which set? Basically, this relation R, okay, on which set we have defined this relation? On which set? What is the base set for this relation? So you can easily see that for this, in this relation you have ordered pairs, right? Correct. In this relation, look at in this relation you have ordered pairs where you have x comma y, means x is related to y. Okay, x is related to y, and you can see that this ordered pair belongs to n square. Okay, this ordered pair, this x comma y, this ordered pair belongs to n square. It simply means that x belongs to n, y belongs to natural number, this n is the natural number, and x is not equal to y. So what is the base set? You can see that natural numbers are related to natural numbers. X is related to y, x is related to y if and only if x is not equal to y. Okay, so here the base set is set of natural number. So remember, the base set is set of natural number. Don't say that this is not the base set. This n square, this is not base set here. Okay, this is not the set on which we have defined the relation. The base set is set of natural number, because you can see that this ordered pair belongs to natural number. It simply this ordered pair belongs to n square. It simply means that this x belongs to n, this y belongs to n. X comma y both are natural numbers, and you can see that x is related to y if and only if x is not equal to y. So here the natural number is the base set. N square is not the base set. Okay. So this is the first thing that you should find it out. What is the base set on which set the relation is defined? Now you can clearly see that this relation is defined on, so this relation R, this is defined on set of natural number. What are the natural numbers? Natural numbers, you can take like 1, 2, 3 and so on. These are the natural numbers. Either 0 is a natural number or 0 is not a natural number. That is your choice. In this question, it does not matter. Okay. So see, there are some authors, there are some writers, there are some mathematicians who will consider 0 as a natural number. So they will consider 0 as a natural number. But there are other authors, there are many other mathematicians who don't consider 0 as a natural number. So whether you take 0 as a natural number or you don't take 0 as a natural number, in this question it does not matter. Okay, In this question, you can take 0 as a natural number. If you want to take this as set of natural number, this is also fine, and this is also fine. The answer will not change. Okay, so you can consider whatever set of basically you can consider 0 as a natural number or not. That both are fine. Both there is no problem in any of the consideration. Okay, so now you have relation on set of natural number. So it means that this relation is from set of natural number to set of natural number. Okay, means element in this set of natural number, this element is related to this element. This element is related to this element if and only if x is not equal to y. Okay, so you can easily see that this natural number is related to this natural number if and only if x is not equal to y. For example, I can say that 1 is related to 2. You can see 1 is related to 3, but 1 is not related to 1. Okay, so every element you can see, for example, I can say 2 is related to 100, but you can notice that 100 is also related to 2, but remember 100 is not related to 100. Okay, so very simple. This is the relation. Now you tell me, is this reflexive? This relation, is this reflexive or not? So this is not reflexive because easily you can see that 1 is not related to 1. You can also see that, for example, 2 is not related to 2. So this is not reflexive. Tell me, is this irreflexive? Reflexive says that every element is related to itself. Okay, this is what reflexive says, that every element should be related to itself. But you can notice 1 is not related to 1. So this is not reflexive. Is this irreflexive? Irreflexive says that no element, okay, no A is related to A. So there is no this type of thing. So no element is related to itself. You can see, yes, this is irreflexive. This relation is irreflexive because in this relation you can notice that for all A, what is happening, for all elements, for all natural numbers, you can notice that A is not related to A. So this is the, I can say that this relation R, so from here I can say that this relation R is irreflexive because you can see no element is related to itself. Okay, what about the next? What about the third property, symmetry? What about this symmetric property? What about this? You can see this is symmetric because if x is related to y, okay, then what it means? It means that x is not equal to y, right? Correct? Okay, so if x is related to y, it simply means x is not equal to y. If x is not equal to y, then definitely y is also not equal to x. Okay, so you can easily see that if x is not equal to y, then y is also not equal to x. So if x is related to y, then y is also related to x. So yes, this is symmetric. The relation is symmetric. What about the fourth property? What about the next property? Can I say this is anti-symmetric? Can I say this is anti-symmetric? The answer is no. This is not anti-symmetric because you can easily see that 2 is related to 3. You can also see 3 is related to 2. So you can notice this is not anti-symmetric. Okay, what about the fourth? Asymmetric. What about asymmetric? See, this is not anti-symmetric. So automatically this is not asymmetric also. Okay, again the same example, you can notice that 2 is related to 3 and 3 is related to 2. So this is not asymmetric also. What about the next? What about the next sixth property, transitive? What about transitive property? Is this transitive? Is this transitive? So can I say that if x is related to y, if A is related to B, B is related to C, then can I say that this will happen? Does it imply A is related to C? Does it imply? The answer is no, because you can see that 2 is related to 3, 3 is related to 2, but 2 is not related to 2. So you can notice that 2 is related to 3, 3 is related to 2, but you can notice that 2 is not related to, this 2 is not related to 2. So this is not transitive. This relation is not transitive. What about equivalence relation? What about equivalence? Can I say this is equivalence relation? The answer is no, because it is not transitive, it is not reflexive. So this is not equivalence relation. What about partial order relation? What about partial order relation? Can I say this is partial order relation? The answer is no, because it is not transitive. Partial order relation must be transitive, anti-symmetric. So this is neither anti-symmetric, nor transitive, nor reflexive. So partial order needs three properties: reflexive, antisymmetric, transitive. None of the property is satisfied. Okay. Equivalence relation needs three properties: reflexive, symmetric, transitive. Symmetric is satisfied, but reflexive and transitive are not satisfied. So you can see this is not equivalence relation, this is not partial order relation. So this is the complete analysis of this question. So finally I can say that this reflexivity is not satisfied, symmetry is satisfied, this is not satisfied, and this is not satisfied. So this is the answer. Only symmetric property is satisfied. Okay. So quite simple this question. Now let's move on. So this is GATE Computer Science 1998 question. So can you solve it? A relation is given to you, binary relation. First of all, what binary relation means? Binary relation simply means that it is a relation between two elements. Okay. You have one element alpha, another element beta. It is a relation between two elements. Okay. So this is called binary relation. Binary relation means relation between two elements. Okay. These two elements can be same, they can be different. So remember, they can be same or different. But anyway, the point is that binary relation means a relation between two elements. Now, this binary relation is given on the set 1, 2, 3, 4. Okay. Now, this relation, as you can see, 1 related to 1, 2 related to 1, 2 related to 2, 2 related to 3, 2 related to 4, and so on. Now, these properties the question is asking. So let's solve it. First of all, let's check for reflexivity. Is this relation reflexive? Is this reflexive or not? Reflexive property says that every element in the base set, this is your base set here. Okay, this relation is defined on A. So this is your base set. Now let's see. 1 is related to 1, 2 is related to 2, 3 is related to 3, but you can notice 4 is not related to 4. So this is not reflexive because 4 is not related to 4. Okay, so this is not reflexive. What about irreflexive? Can you tell me what about irreflexive? In this question, what can you say about the irreflexive property? What can you say about that? This is not irreflexive because you can easily see 1 is related to 1. Okay. Irreflexive says that no element should be related to itself. But you can notice 1 is related to 1. What about symmetric property? What about this symmetric property? You can see that 2 is related to 1, but 1 is not related to 2. Okay, 2 is related to 1, but okay, so you can see this is not symmetric because 2 is related to 1, but you can notice that 1 is not related to 2. Okay, so definitely this is not a symmetric. What about the next property? So we have seen three properties. Now let's see what about antisymmetric property. What can you say about antisymmetric property? You can see 2 is related to 1, but 1 is not related to 2. Antisymmetric says that different elements must not have symmetry. Okay. So different elements, they must not have symmetry. You can see 2 is related to 1, but 1 not related to 2. Next, 2 related to 3, 3 related to 2. So this is not antisymmetric. This is not antisymmetric because 2 is related to 3 and 3 is related to 2. So this is not antisymmetric. Now let's see asymmetric. Asymmetric. Remember, not antisymmetric automatically implies not asymmetric. You can see that this is not asymmetric because the reflexive pair is also not allowed. This is the reason. The reflexive pair is also not allowed. Either you can take this reason or you can take this reason that 2 related to 3, 3 related to 2. So this is not asymmetric. Okay. Now, what about the next? Transitivity. For transitivity, you create a graph. If you want to check for transitivity, the best way is create a graph representation. This is the best way to check. So there are 4 elements, 1, 2, 3, 4. These 4 elements you have. Now you create the graph. The graph is like this. 1 is related to 1. Then 2 is related to 1, 2, 3. Sorry, 2 is related to everyone. Okay, 2. This 2 is related to everyone. You can see that 2 is related to everyone. 2 related to everyone. Okay, now what next? 3 is related to everyone. Okay, so again this 3 is also related to everyone. Now let's check, is this transitive? This relation, is this transitive relation? So first of all, for transitivity you can notice that if A is related to B, B is related to A, then definitely this must happen. And this is happening here. Okay, in this relation, this thing is happening. So there is no problem here in this situation. There is no problem. What about the next? Okay, you can notice 2 related to 3, 3 related to 2, and they are also there is self loop also. So there is no problem here. So this condition is satisfied. Now the other condition is this, that A related to B, B related to C, then A must be related to C. Is this property satisfied? You can see that. Let's check it out. So here this property here is satisfied. 3 is related to 2, 2 related to 4, 3 related to 4. Here also it is satisfied. Okay. So, okay, correct. So this is a transitive, right? Yes or no? So this relation is transitive because you can easily see that all the properties are satisfied. This property is also satisfied. A and B, they are related to each other. A related to B, B related to A. Then A must have self loop, B must have self loop. And this is happening here. Okay, this is happening here. You can notice. Okay, you can easily see here in this. So 2 related to 3, 3 related to 2. 2 has self loop, 3 has self loop. So this is satisfied. You can also see that that 3 related to 2, 2 related to 4, 3 related to 4. Similarly, you can see that 2 related to 3, 3 related to 4, 2 related to 4. So all these properties are basically satisfied. So this is transitive. So this relation is a transitive. Yes, transitive property is satisfied. So finally I can say the answer will be, this is a not reflexive, neither reflexive nor irreflexive, but transitive. So answer will be option B. Irreflexive, symmetric, this is not symmetric. You can easily see that the relation was not symmetric. So this option is gone. You can notice this is not reflexive, this option gone, this option gone. This is not irreflexive, this option gone. Answer will be option B. Okay, so this is a simple question. What about equivalence relation? What about equivalence relation? Equivalence relation means reflexive, symmetric, transitive. But you can notice this is not reflexive, not symmetric. So this is not equivalence relation. What about partial order relation? What about partial order relation? Can I say this relation R is partial order? The answer is no, because it is not reflexive. It is not anti-symmetric. Okay, so that is the reason this is not a partial order relation. So these are the properties of this relation. Very easily you can see. Let's see this one. The binary relation, the empty relation on set 1, 2, 3. What properties does this have? Empty relation, you have empty relation on set 1, 2, 3. What properties it will have? So you can easily see that if you have any non-empty base set, it may be 1, 2, 3 or any. Basically this A can be any base set, any non-empty base set. By default base set is always non-empty. Okay, so this can be any non-empty base set. This A, it can be any non-empty base set. Now you can see that on this, if you define a relation, empty relation, this empty relation, if you define this relation empty, you define on A, then what properties it will have? You can easily see this will not be reflexive. This will not be reflexive because you can see 1 is not related to 1. So this is not reflexive. What about irreflexive? What can you say about irreflexive? Irreflexive says that no element is related to itself. So this is satisfied. Okay. What about symmetric? Symmetric is also satisfied because there is no violation of symmetry. There is no violation of symmetry. Okay. What about anti-symmetry? Anti-symmetry is also satisfied. There is no violation of anti-symmetry. Asymmetry is also satisfied. There is no violation of asymmetry. And similarly, there is no violation of transitive. So the only violation happens for reflexivity. This is the only violation happens. Okay, because 1 is not related to 1. This is the only violation that happens. There is no other violation. There is no violation of transitivity, no violation of asymmetric, no violation of antisymmetric. Okay, no violation of irreflexive. So you can see that the only violation happens is the property reflexive. So this is not reflexive. All other properties are satisfied. So the answer is going to be, this will be transitive and symmetric. Okay, so the answer is going to be option D. So this is a simple question, that if you have empty relation on non-empty set, by default your base set is always non-empty. Remember, your base set on which you are defining the relation, by default it is always non-empty. As I told you, that domain is always non-empty by default. In the whether you study mathematical logic, first order logic, or set theory, the domain, okay, on which you are defining the relation, that domain that base set is always by default non-empty. So if you define empty relation on non-empty base set, then reflexive property will be violated because 1 is not related to 1. The remaining properties have no violations. So you can notice all these remaining properties, if you notice, all these remaining properties basically they are trivially satisfied. Okay, these properties are basically trivially satisfied because there is no violation. Okay, because there is no violation. Because of no violation, these properties are trivially satisfied. Okay, let's move on. Now let's see this question. The question number 4 in GATE Computer Science 2009. Again, a binary relation is given to you. In this relation, on set XYZ, which properties are satisfied? So you tell me, one by one, you tell me. First of all, what about reflexive property? On this set, this is your base set. On this set, you are defining the relation R. So you can see that X is not related to X. So this is not satisfied. Reflexive property not satisfied because X is not related to X. What about irreflexive? What about irreflexive? Irreflexive says that no element is related to itself. No element, yes, no element is related to itself. So yes, this is satisfied. This is satisfied. Okay, what about symmetric property? What about symmetric? Symmetric means X is related to Y, so Y should be related to X. So this symmetric property is not satisfied because X is related to Y. You can notice that Y is not related to X. So this is not satisfied. What about antisymmetric? What can you say about antisymmetric property? Antisymmetric property, you can see that because of this antisymmetric property is violated. Antisymmetric property says that different elements must not have symmetry. Okay, different elements, like these are different elements, so different elements must not have any symmetry. So you can see that this X is related to Z, Z related to X, so this is also violated. So this antisymmetric is also violated because X is related to Z and Z is related to X. Okay, what about the next property, that is asymmetric? What about asymmetric? If it is not antisymmetric, automatically it is not asymmetric. Okay, so this is useful result that if you have not antisymmetric, if your relation is not antisymmetric, then it simply means it is not asymmetric also. Okay, but this direction is not correct. This direction does not hold because remember, in asymmetric you can't allow the I can say reflexive pairs. Okay, so in the asymmetric we don't allow reflexive pairs, but in the antisymmetric reflexive pairs may be present. Okay, now so this is not asymmetric. What about the transitive property? For the transitive property, the best way is create the graph X, Y, Z. Create the graph here. So you can notice X related to Y. Next, X related to Z, Z related to X, and Z related to Y. Here, what is the violation? See, easily you can see the violation here. Very easily you can see the violation. Very easily. Look at this violation. Because you can notice X related to Z, Z related to X. So transitivity says that X must have self loop, Z must have self loop, but that is not satisfied. So you can easily see this is not transitive. Okay. So this is something important, that you can see that if X is related to Z, Z is related to X, then what should happen? Then X should be related to Z. Similarly, if Z is related to X, X is related to Z, then this should happen that Z is related to Z. So whenever this happens, that X related to Z, Z related to X, then transitive arrows are these. These are the transitive arrows. Okay, so these are the transitive edges. So you can easily see this is not transitive. The relation is not transitive. Okay. So finally, the answer is going to be the relation is not symmetric and the relation is not antisymmetric. So neither symmetric nor antisymmetric. The answer will be option D. Okay. And what about equivalence relation? This is not equivalence relation because it is not symmetric, it is not reflexive, it is not transitive. What about a partial order relation? This is not partial order relation because it is not antisymmetric. Okay, so neither equivalence relation nor partial order relation, this relation. Let's move on. Let's see this question. This is a GATE 1996 question. Okay, The question is saying that R is non-empty relation, okay, on a collection of sets. This is important. Look at this. On a collection of sets, there is some collection of sets, okay, and R is non-empty relation on this collection of sets defined by A is related to Y, A is related to B if and only if A intersection B is phi. Means A is related to B if and only if they are disjoint. Okay, A is related to B if and only if A comma B are disjoint. A comma B are disjoint. So disjoint sets are related. First of all, this option you can very easily you can cross, because reflexivity transitivity is a property of a relation, not a property of element, right? Correct? Are you getting my point? So you can very easily remove this option. Because why this option? Because remember, this reflexivity, this transitivity, etc., these are properties of relations. These are properties of relations. Okay, so all these are properties of relations, not of individual elements. Not of individual elements. Okay, so this is something that we have already seen in the last lecture. In the summary lecture, we have already seen this. Do you remember? Do you remember what question we had? The Stanford question. Do you remember that? Stanford University question. I took one question in the last lecture, in the summary lecture of relations. I took one question where you can easily see that this was Stanford question, that you can see that reflexivity, transitivity, etc., these are properties of relations. These are not of individual elements. So this option A is gone. Okay. Now let's see the remaining options. Now remember, tell me simple thing I am asking. If R is non-empty, this R is a relation. Okay, this R is non-empty. So what can you say about base set? Definitely base set is also non-empty. Do you agree? Do you agree that R is non-empty? If R is non-empty, then automatically means that the base set is also non-empty. The base set is also non-empty. Correct? Okay. So very easily you can see, because relation is non-empty, then definitely base set is also non-empty. Now you have a base set, collection of sets. So your base set, let me call the base set as S. So I am calling base set is S. In this base set, what we have? This is a collection of sets. This base set is a collection of sets. So this base set is collection of sets. Remember, the question is saying that on a collection of sets. Okay. So this base set is your collection of sets. In this you have some sets like A, B, and so on. All these are sets. So like this is a set, and so on. Okay, and so on. So this S is a collection of set. Some collection of set is this. Now tell me, and we are defining this relation R. On set S, and we are saying that this A is related to B if and only if A intersection B is a phi. If and only if they are disjoint. Okay, I can say if and only if A comma B are disjoint. I can simply say that if and only if A comma B are disjoint. Okay. So now you tell me, this is something like we are defining a relation R. So you have a set S. This, what word the question is using? The question is using the word that this is a collection. We don't know which collection of set, right? This is a collection of sets. So in this S you have some sets you have. Okay, some sets you have. We don't know which sets you have. So this is a collection of sets. Okay, and you are defining this relation R on S. Okay, now you tell me this is non-empty. We already know. So what can you say about reflexive property? What can you say about reflexive property? Can I say that A is disjoint from A? Can I say A is disjoint from A? So reflexive property. What about reflexive property? What about reflexive property? See, this reflexive property may be satisfied. Remember, this may be satisfied. Why? If you take a particular S, if you consider this S in which you have only empty set. consider this S. If your S is this, if your set S, because this is a collection of sets, the question is saying S is a collection of sets. So if S is this set, then automatically means that reflexive property for if S is this, now if you define R on S, okay, then definitely this will be reflexive, right? Then this will be reflexive. Is this clear? Tell me, are you getting my point what I am saying? Please read the question. The question is saying on a collection of sets. You are defining this relation on a collection of sets. You are defining this relation, you are defining on a collection of sets. So this is something that you should focus. You are defining the relation on a set S, on a collection of set S. So if your set S is this, then in this situation it will be reflexive. Okay. But apart from this, in general, what will happen? In general, what will happen? Tell me. Like if this happens, then reflexive property will be satisfied. Okay. But in general, what will happen? In general, if you take some S, like this will not be true for all S. Like in general, if you take some S, okay, like for example, if S is like this, for example, phi, and let's assume this set 1, 2. If this is your set S, then in this situation, you can definitely see that, let's call it A. Then you can notice that A intersection A is not phi. Okay, so A is not disjoint from A. So I can say that A is not related to A. So in this situation, you can see reflexive property will not be satisfied. Correct? So this will not be satisfied. So in this question, actually, in general, basically this reflexive property in general, it will not be satisfied. Okay. So it will actually depend on what is this set S. It will actually depend on that. But in this question, from the options, you can easily see that we have to take the general scenario. Okay. The question is asking, if you see the options, you can see that the question is asking for a general scenario. So the reflexive property is not satisfied. Is this point clear? Let me know. So in general, you can notice that you are defining this relation. So in general, it happens. In general, you can notice that if you take A intersection A, that is not phi. Okay. If unless A is equal to phi. Okay, so in general, you can notice that this is not equal to phi. So in general, I can say that A will not be related to A. This A will not be related to A, so not reflexive. So this will not be reflexive. Okay, so here this relation is not reflexive. Now, what about the next property? What about the next? But can I say it is necessarily like whatever set you take, can I say it is not reflexive? See, this will be a nice question if I ask you. This is going to be a nice question that can I say for every S? Can I say for every S? Can I say R is not reflexive? Can I say? Can I say for every S? Can I say that for every set S, for every collection of set, can I say R is not reflexive? The answer will be no. The answer will be no, because you can take this collection of sets you can take. Now, if you define R on this S, then that will be reflexive. Okay. So very easily. But remember, if you take some other S, if some other set S you take, for example, if you take this set S, as I told you, like A, B, C. So if you take this S or some more, then in this situation, let's call it A. Then in this situation, if you define R on S, then that will be not reflexive. So this will be a nice question that can be created. Okay. Now let's see this. What about symmetric, anti-symmetric? What can you say? Disjointness, is it symmetric? See, this will always be symmetric. Disjointness is always going to be symmetric. Can I say it will always be symmetric? Like for every S, can I say R is symmetric? The answer will be yes. Okay, whatever S you take, whatever set you take, this will always be symmetric. The symmetric property will always be satisfied. Disjointness is always symmetric. Okay, whatever you take, this will always be symmetric. So this will be symmetric here also, whatever you do, this always will be symmetric. So this relation, you can see this relation R on S you define. Okay, and this will always be symmetric, this disjointness, because you can see, look at the symmetric property. You can see that if A is related to B, then definitely B will be related to A. Because what this means that A intersection B is phi. So definitely B intersection A also will be phi. Okay, so this symmetric property is always satisfied. Whatever set you take, this symmetric property is always going to happen. Okay, because you can notice disjointness is always symmetric, right? If if A intersection B is phi, then definitely B intersection A will be phi. If A is related to B, then B will be related to A. Is this clear? So you can easily see, if you want to see symmetric property, why symmetric property is satisfied, let's see this set you have. You can take any set, whatever set you want. For example, consider this set. Now you can easily see, you can easily see that this intersection, this is a phi. So automatically this also will happen, that this intersection, this also will be phi. So symmetric property will always be satisfied. If A comma B are disjoint, then B comma A also will be disjoint, right? Yes or no? You can easily see that if A comma B disjoint, then B comma A will be disjoint. If A comma B disjoint, then definitely B comma A will be disjoint. Okay, so definitely symmetric property is always satisfied. Is this clear? Let me know. Now let's move on. Now let's see the next property, that is transitive property. What can you say about transitive property? Again, it will depend on the set S. Okay, it is going to depend on the set S, that this basically whether this is transitive or not. So it will again depend on the set S, like what is your set S. But you can notice in general, this transitive property may or may not be satisfied. Okay, so this may or may not be satisfied. This transitive property may or may not, depending on S. Depending on S. For example, if your set S is this, like let me take the set S. Consider this set S. Like for example, here you can see that, let's assume this is the set S. Now in this set S, you can easily see, on this if you define relation R, then that will be transitive, right? That is going to be transitive. Okay, that will be transitive. But the same situation if I do, for example, if I define this, if I take this set S, then you can notice this will be not transitive. Okay, now this relation R will not be transitive. So now this is not going to be transitive. Okay, so again it will depend on S. So in general I can say it is not transitive, right? Correct? Is this clear? So in general I can say that this relation R on S you are defining, in general not transitive. In general this is not transitive. But remember, it may be transitive depending on what is S. What is the set S? Depending on that, it may be transitive. Okay, so these are the properties. These are all the properties that we have seen. Now in this question actually, I can say there is some small mistake actually, because of this. But anyway, you can find the answer without any problem. You can say that this is always going to be symmetric. So the question is saying that, okay, so this is not transitive. So the answer is symmetric, not transitive. So the answer will be option B. This is the best option. Okay, it will be symmetric. Whatever you do, the relation will definitely be symmetric. So the option B is the best suitable answer. Okay, is this clear? Tell me, the analysis of this question, is this clear? Let me know. The analysis is clear or not? Some good question can be created. See, why this question is important, let me tell you. Because some good question can be created, like this type of question can be created, that S is some set, and this type of question can be created like for all S, for all possible X, what can you say about R? Okay, some good quality question can be created. Okay, for all possible S, what can you say? So for all possible S, I can say it will be symmetric. Whatever S you take, it will be symmetric. The symmetric property is not going anywhere. Okay, it will be symmetric. But for all possible S, we cannot say it will be transitive or other properties. It will definitely be symmetric. In the question, base set is given. First of all, you focus on the base set. the base set is given as a collection of set. Okay, this base set is a collection. This is a collection of sets. Okay, this is this base set. So your base set is collection of sets. Like in the base set you have all the sets. Sorry, not all the sets, but some collection of set. So for example, this is a set. For example, this is a set. This is also a set, and so on. This is your base set. You are defining relation R on S. If you are defining relation R on S, then elements of S will be related to elements of S. Correct? Yes or no? Elements of S will be related to elements of S. Now the question is saying that if you take two elements here, if you take two elements like X belonging to S, Y belonging to S, then when can you say that X is related to Y? X is related to Y if and only if X intersection Y is phi. Okay? So this is given, means when they are disjoint, then they are related. Is this clear? See, when they are disjoint, then they are related. The question is saying that you are defining a relation from S to S. Elements of S are related to elements of S. So if you take two elements of S, same or different, if you take two elements, then when can you say they will be related? They will be related if and only if they are disjoint. Like for example, if your set S is this, consider the set S is this. Let's assume A comma B, and let's assume this is C. Now in this situation, let's call it A, let's call it B, let's call it C. In this situation, you can notice that A is not related to B because they are not disjoint. You can notice A is related to C. You can notice B is related to C. You can notice B is not related to A because they are not disjoint. You can notice C is related to A. You can notice C is related to B. Please tell me, is this clear now? Is the question clear what the question is saying? So if your set S is this, then you can notice that symmetric property is always satisfied. Okay, so this, like you can notice symmetric property is always satisfied. This. So definitely you are defining this relation and that always will be symmetric. Now let's move on to the next question. So in this question, actually this could have become a nice question, let me tell you. At this point of time, this is not a good question. At this point of time, because as you see, you can get the answer, of course. Of course, the best suitable answer is option B. That is the best possible choice. But what I'm saying that this can be created into a good question. Okay? Like if they say that for all collection of sets, like whatever collection of set you take, then what will happen? Okay? So this can be created, this can be converted into a very good question. But at this point of time, you can get the answer, and the best choice of the answer is option B. Okay, let's move on. Now let's see this question number, this GATE Computer Science 2015 question. So let's see this one. Relation R on set of ordered pairs. Okay, what is the base set? First of all, you tell me what is the base set. Look at this. On the set of ordered pairs of positive integers. What this means? What this means? On set of ordered pairs of positive integers. It means on Z cross Z. Positive integers. Positive integers means on n cross n. So this relation that you have defined is on n cross n. So your base set, remember your base set is this. Please understand that your relation is defined on set of ordered pairs of positive integers. So your base set is defined on n cross n. So this is something very important, that you are defining relation R on n cross n. Okay, on n cross n. So this n cross n is the base set. On this you are defining the relation. It means elements of n cross n will be related to elements of n cross n. Okay, is this clear? Elements of n cross n will be related to elements of n cross n, because the question is saying that positive integers. Positive integers means you can say set of natural numbers. So this is something very important, that this will happen. Okay, it simply means that this R is a subset of what? This R is a subset of n cross n cross n cross n. Or you can say that R is a subset of n cross n power 2. Okay, so this is what you can say, that R is subset of this. So this is something very important, that elements of this set elements of this n cross n, they are related to elements of n cross n. This is what the question is saying. Okay, because you are defining relation on set of ordered pairs of positive integers. So please focus on this one, this line. You focus on this line. Okay, now let's move on. Now the question is saying that this ordered pair is related to this ordered pair if and only if p minus s is equal to q minus r. P minus s is equal to q minus r. Okay, so first of all, you understand the question. Before solving the question, you should understand the question, what the question is saying. So the question is saying that a relation you are defining from n cross n to n cross n, elements of n cross n are related to elements of n cross n, and the question is saying that if you have some element like p comma q, this is related to r comma s. Okay, p comma q, that is related to r comma s if and only if p minus s is equal to q minus r. This is what the question is saying. So this is happening if and only if p minus s is equal to q minus r, or you can say that p plus r is equal to q plus s. Okay, so either you can say this, or you can say that p plus r is equal to q plus s. So this p plus r, this is equal to q plus s. This is what the question is saying. First of all, you understand the question very clearly. What the question is saying, actually this is saying that like in this n cross n, you take some element in this n cross n. So you can take, for example, 2,5 you can take. This is related to what? You can notice that this addition should be equal to this addition. Okay, this p plus r, this should be equal to q plus s. This is what the statement is saying. Okay, so you can note this plus this should be equal to this plus this. So I can say, for example, if I take 8 here, then what should I take here? Can you tell me what this will be? Can you tell me what this will be? What this is going to be? So you can easily see that 2 plus 8, what this is going to be. So you can easily see that this 2 plus 8, 10, this should be equal to 5 plus, so this must be 5. Okay, this must be 5, correct? This must be 5. So very simple. So this is what I am saying, that first you understand the question clearly, that you can see that 2,5 is related to 8,5. You can easily see that p minus s is equal to 5 minus 8. 2 minus 5 is equal to 5 minus 8. So very simple. Similarly, you can notice that 2,5, this is definitely, can I say this is related to 2,5? Can I say this is related to 2,5? Can I say that this plus this is equal to this plus this? The answer is no. So you can easily see this is not reflexive. Immediately you can see this is not reflexive. The relation is not reflexive. Okay, because this is the element, this element is not related. Let's call it x. This is not related to x. X is not related to x. So you can clearly see that this is not reflexive. This relation is not reflexive. Okay, so and so on. So I hope this point is clear, that what is this question? I hope you understood. Like whatever you take, for example, I can say 11, 20, that is related to what? I can say that is related to 1, I can say this is not related. See, 11, 20, this is not related to 1, anything. If you take 1, anything, whatever you can put anything. Okay, you can put whatever you want to put. You can put anything. This x can be any. This x can be any natural number. Okay, so this will not be related. So you can see, because 11 plus 1, that is 12. This will never be equal to 12 plus x. Okay, that is never going to be equal to 12 plus x. So definitely this is not related to 1, x. X can be any number. So once you understand the question, okay, now let's just remove it. So let's use this. Let's use this, that p plus r must be equal to q plus s. Let's use this. So p plus r must be equal to q plus s. We will use this one. Okay, p plus, you can notice p plus r will be equal to q plus s. So now using this, can you solve it? Now what about the reflexive property? Let's see one by one. What about the reflexive property? What can you say about the reflexive property? The reflexive property is not satisfied, because if you take some element in n cross n, you take a comma b belonging to n cross n, you take some element in the base set. This is your base set. This is element in the base set. This is element in the base set. So you can easily see that a comma b may or may not be related to a comma b, right? Okay, so this may or may not be related to a comma b, may or may not. Okay, so you can easily see like what I'm saying. For example, you can see that this 1 comma 3, this is not related to 1 comma 3. Okay, but remember, so this is not reflexive. What about 1 comma 1 related to 1 comma 1? This is true, right? So this is not irreflexive. So not irreflexive. So you can say that are not reflexive. So not irreflexive. Yes or no? So this is not reflexive and this is not irreflexive. This relation is neither reflexive nor irreflexive. Okay. Now this is the first thing, that reflexive, irreflexive both are false. What about the next? The third one, what about symmetric? Can you say it is symmetric? Like, can I say if this is related to this, means if this happens, that this addition this is equal to this addition this, then can I say, means if p plus r is equal to, if this happens, that so if p plus r is equal to q plus s, then can I say r comma s will be related to p comma q? Can I say that? Can I say r plus p will be equal to s plus q? Yes, right, because r plus p will be equal to s plus q. So if this happens, then this will happen. Okay, so this will happen, then this will happen. So symmetric property is satisfied. So yes, this is symmetric. Symmetric property is satisfied. Yes or no? Very simple. You can see that if PQ is related to RS, so it simply means that this will happen. So if this is happening, then definitely this will happen. Okay, so if P plus R is equal to Q plus S, then definitely R plus P equal to S plus Q. Okay, so very simple. So if this element is related to this element, then definitely this R comma S element will be related to P comma Q element. So this is symmetric property. Okay, so this is symmetric. What about the next? Let's look at the antisymmetric property. What can you say about antisymmetric? So this is not antisymmetric, right? This is not antisymmetric because you can see that 2 plus 3 is related to 5. You can see 2 plus 3, that is related to what? That is related to 5 comma 4, and 5 comma 4 is related to 2 comma 3. So you can easily see that this is not antisymmetric, and not antisymmetric automatically means not asymmetric. It automatically means this is not asymmetric also. Okay, so because as you know that the same example will work, the same counter example you can put here, the same counter example you can use here. So the same counter example will work here also. Okay, let's move on to the next, that is transitive property. What can you say about transitive? What can you say about the transitive property? See, the transitive property says that if P, okay, let's A comma B. So for example, if A comma B is related to C comma D, okay, so that is related to C comma D. And let's assume that C comma D is related to E comma F. So what it simply means, then can we say, simple question I am asking, then can we say that A comma B will be related to E comma F? If this happens, if this and this happens, this happens and this happens, if these two happen, then can I say A comma B will be related to E comma F? So let's check it. So here you can notice that A plus C is equal to B plus D. So A plus C, that is equal to B plus D. Okay, and here you can see that C plus E is equal to D plus F. Okay, so can we say from this, can we say that A plus E will be equal to D plus F? Can we say that? What about this? So A plus E. So that is what we have to check. So from here, can we say that A plus E is equal to B plus F. This can we say. So what you do, for example, you can add both of them. Okay, so let's add them. Let's add. If you add them, then what you will get? You will get A plus 2C plus E is equal to B plus 2D plus F. Okay, so can we say that A plus E will be equal to B plus F? It may not happen, right? Yes or no? It may not happen that A plus A plus E equal to, so this may not happen. See, this will happen. You can notice A plus 2C plus E, that is equal to, so this may not imply this. This does not imply this one. Let's take a concrete example. Let me take some concrete example. Let me take, like, for example, you can see. So let's take a concrete, like you can see that 1 comma 2 is related to 2 comma 1, or I can say 1 comma 2 is related to 3 comma 2, and you can notice 3 comma 2 is related to what? That is related to 4 comma 5. Then can I say that what about 1 comma 2? Can I say that is related to 4 comma 5? Can I say 1 plus 5 is equal to 1 plus 4 is equal to 2 plus 5? This is not true. Yes or no? This is not true. You can notice that 1 plus 4 is not equal to 2 plus 5. So definitely I can say this is not transitive. The relation is not transitive. Okay, but did you understand the proof? See, tell me, did you understand the intuition what is happening here? I am assuming that AB is related to CD. CD is related to EF. I am assuming this. Now, from this I am getting this equation. I am getting this equation that A plus 2C plus E is equal to B plus 2D plus F. But from this I cannot conclude this. Okay, this I cannot conclude, right? Yes or no? From this equation, I cannot conclude this equation. So definitely I cannot conclude this equation. So that is the reason I am saying that this is not transitive. And you can take a concrete example like 1 comma 2. Like you can see that this 1 comma 2, this is related to this. Okay, this is related to this one. But you can notice that this 1 comma 2 is not related to 4 comma 5. This is not related to that. So that is the reason I can say this is not transitive. The relation is not transitive. Okay. So finally, what are your in this question? So you can easily see that in this question, reflexive property not satisfied, irreflexive property not satisfied, symmetric property is satisfied, antisymmetric property is not satisfied, asymmetric property is not satisfied, and transitive property is not satisfied. So this is your question. Now you can find out the answer. So the answer is saying reflexive. This is not reflexive. This is symmetric but not reflexive. Okay, so this is a symmetric but not reflexive. The answer will be option C. Okay, answer is going to be option C. Now, Twinkle is asking some doubt. So let me take that. Twinkle is asking about asymmetric, antisymmetric. Can you please repeat about the relation being anti? So this is not antisymmetric because see, in this relation you can notice this is not asymmetric. This relation R, this is not asymmetric. Why this is not asymmetric? This is not asymmetric because you can easily see that this 2 comma 2, this element is related to 2 comma 2. Right. So this is not asymmetric. Twinkle, correct? You can see that 2 comma 2 related to 2 comma 2. So this is not asymmetric. This is the counter example. This is the counter example. Similarly, this relation is not antisymmetric. This relation is not antisymmetric. Why this is not antisymmetric? Because you can see that 2 comma 3 is related to 3 comma 2. Okay, and you can notice 3 comma 2 is related to 2 comma 3. Okay, so they are basically related. So that is the reason this is not this is the counter example for antisymmetric. For antisymmetric, this is the counter example. The same counter example will work for antisymmetric also. For asymmetric also the same counter example is going to work. See, this is the statement. If something is not antisymmetric, If something is not antisymmetric, then that is automatically not asymmetric. Or I can say if something is asymmetric, then that is automatically antisymmetric. Okay. So, but these are one-way statement. This does not mean this. So these are one-way statement. Okay. If something is asymmetric, it is automatically antisymmetric. And asymmetric is a strict condition, very strict condition. This is very strict. This does not allow reflexive pairs. Okay, does not allow reflexive pairs. This does not allow reflexive pairs also, but it allows reflexive pairs. It allows reflexive pairs. So if something is asymmetric, that it is automatically antisymmetric. Is this clear, Twinkle? Please tell me. In this question, all the doubts are clear. Now let's see this question. So did you notice that base set, finding base set is very important, right? Yes or no? In any question, finding base set is very important. So whenever you solve any question related to, okay, so in the relation questions, in relations, base set is very important. Okay, finding base set, what is the base set, on which set you are defining the relation. This finding base set is very, very, very important. So don't make the mistake here. Okay, let's move on. Now let's see this question. This is GATE 2016 question. Can you tell me what is the base set before you solve this question? So you have a relation R, you have a binary relation R on n cross n. Look at this. You have a binary relation R on n cross n. What it simply means, your relation R is on n cross n. It simply means that you have a relation which will relate elements of n cross n will be related to elements of n cross n. Okay. So this is what is happening. It simply means that R is a subset of n cross n whole square. Okay. R is subset of that. So this is a something that, like, this is your base set. So in this question, the n cross n is the base set. So this is something that you have to find out. Okay. N is not the base set. Your base set is n cross n because you are defining relation on n cross n. See this, relation on n cross n. The relation is defined on n cross n. Okay, on n cross n. Now, so the question is saying that a comma b is related to c comma d if a is less than equal to c or b is less than equal to d. Either a is less than equal to c or b is less than equal to d. Now some questions, now some good questions the question is asking. But before that, you understand this relation. So you have this relation R on n cross n. Okay, on n cross n. What it simply means, it means that your relation is from n cross n to n cross n. Elements of n cross n are related to elements of n cross n. And in what fashion? In this fashion that if some element you take here like x comma y, that is related to, if you take some element here that is related to z comma m. Okay, if and only if what is happening, that is happening if and only if either x is less than equal to z or y is less than equal to m. Okay, so this is what that is given to you in this question. Now for example, you can see that I can say 2 comma 5 that will be related to 3 comma 4 because this 2 is less than 3. Similarly, you can notice this 2 comma 5, this is also related to 10 comma 20. Okay, because the condition is satisfied. You can see that 2 comma 5 is not related to 1 comma 4. Okay, so this 2 comma 5 is not related because you can notice that 2 is not also, and you can notice 5 is not less than equal to 4. So this is something that you have to understand, that what is related to what, which elements are related to which elements. So you can notice 2 comma 5 related to 3 comma 4, 2 comma 5 related to 10 comma 20. Similarly, 2 comma 5 is related to 1 comma 11. That is also fine because 5 is less than equal to 11. Okay, so this is how you can see that which elements are related to which elements. Now let's see all the all the properties. Now let's see. Now let's do the complete analysis of this question, that again a comma b is related to c comma d if a is less than equal to c or b is less than equal to d. Okay, now tell me the reflexive property. Is that satisfied? Is the reflexive property satisfied? What about the reflexive property? The question, in the question you can notice, of course, reflexive property will be satisfied. It will be satisfied because a comma b definitely will be related to a comma b. Okay, so you can easily see it will be related to this because this is less than equal to this. So definitely this is a related. Okay, so this is reflexive. What about irreflexive? So this is definitely not irreflexive. The same example you can take, for example, 1 comma 2 is related to 1 comma 2. This is the counter example. Okay, this can work as the counter example. So you have counter example that this is not irreflexive. Okay, what about the next property? What about the symmetric property? What can you say about symmetric property? Is this symmetric? Can I say that it will be symmetric? It will not be symmetric. It is not going to be symmetric. For example, you can easily see that 2 comma 5 that is related to 10 comma 20, but you can notice that 10 comma 20 is not related to 2 comma 5. Yes or no? So you can easily see that 2 comma 5 is related to 10 comma 20, but 10 comma 20 is not related to 2 comma 5. So this is not symmetric relation. What about anti-symmetric? What about anti-symmetric? What can you say about anti-symmetric property? What can you say about the anti-symmetric property? Again, this is not anti-symmetric. Again, you can see that, for example, this 2 comma 5, you can notice this is related to 3 comma 4, right? And you can also see that 3 comma 4 is related to 2 comma 5. Okay, so you can notice this element is related to 3 comma 4, and so you can easily see that 3 comma 4 is related to 2 comma 5. So this is not anti-symmetric also. This is not symmetric. This is not anti-symmetric. Automatically means that this is not asymmetric also. Yes or no? Automatically means that this is not asymmetric. Because if it is not anti-symmetric, then it is not asymmetric. So this relation is not asymmetric also. The same counter example will work, or you can use this counter example that 1 comma 1 is related to 1 comma 1. You can use this counter example also. So you can this counter example will also work. Now let's move on. What about the transitive property? What can you say about the transitive property? What can you say about that? See, the transitive property, let's check. If a comma b is related to c comma d, and let's assume that is related to e comma f, then what it means? Then it means that either one of these things can happen. See, you can easily create a counter example for transitivity. Maybe this happens. See. Maybe this happens here. Okay, maybe this happens here. But you can easily see that there is no reason that this must happen, or I can say this must happen, right? So you can notice this transitivity will be violated. This transitivity you can easily violate. For example, for the transitivity, what you can say? For the transitivity, you can easily violate, and you can violate like this. You can say that, see, 3 comma 6, that is related to 2 comma 8. That is related to, or I can say 1 comma 8. Okay, so 3 comma 6 is related to 1 comma 8, and that is related to 2 comma 5, right? So you can see very easily, you can create a counter example. So like this, you can see that here 6 is less than equal to 8. So these are related. And here you can notice 1 is less than equal to 2. So these are related. But you can easily see that 3 comma 6 is not related to 2 comma 5. Okay, so you can easily see these are not related. 3,6 is not related to 2,5. So this is not transitive. The relation is not transitive. So all the properties we have seen. Now you tell me the answer. The relation is not transitive. The relation is reflexive. So the answer will be, which is true, the question is asking. So P is true, Q is false. P is true, Q is false. The answer will be option B. The question is asking for true. Okay. So this is your answer. Now let's move on to the next question. This is something interesting, and this is one of very good question, good quality question. I will tell you why this is a good quality question, because in this question some other result can be created. What the question is saying, this is a GATE 1999 question. There is a Mr. X who is claiming the following. He is saying that if a relation is both symmetric and transitive, then it must be reflexive. Okay. Now what Mr. X is saying, Mr. X is giving a proof. He is giving a proof that, see, reflexive and transitive. So you can notice, if X is related to Y, then symmetry you use, then you can say Y related to X. Now X related to Y, Y related to X, then by transitivity X related to X, and that is the reason reflexive. So it seems like a very good argument. Argument is very good. There is no problem in the argument, because we already know. See what this argument is saying. You can notice the part A. There is a Mr. X. Okay, what this Mr. X is saying, this Mr. X is saying that if you have symmetric and transitive, then from this you can say that relation will be reflexive. And the argument is this. What is the argument? The argument is that, see, if X is related to Y, okay, then automatically by symmetry it means Y related to X. Okay, by symmetry Y will be related to X. Now you can notice that X related to Y, Y related to X. By transitivity, what will happen? By transitivity, X related to Y, Y related to X. By transitivity, X related to X, Y related to Y. So reflexive. So reflexive. What is the problem in this argument? Can you tell me? In this argument, what is the problem in this argument? It looks very good. The argument looks very good. A beautiful argument. But what is the problem in this argument? So let me tell you, this argument is wrong. Why this argument is wrong? The argument is wrong because this may not happen, right? The problem is here. See, the problem is here. This may not happen. You may not start. See, of course, if you start, if you start, then definitely everything is correct. Okay. If X relates to Y, then no problem. Okay. If X is related to Y, then there is no problem. But you may not start. X may not be related to Y. Okay. So the argument is wrong because of this point. At this point of time, argument has become wrong. This may not happen. Yes or no? This may not happen in the first place. This may not happen in the first place, right? Correct? So this may not happen in the first place. You can notice. For example, let me give you example, like consider this set, a base set I am giving, like A, B, C, D. Consider this base set. In this base set, you can see that if, let's assume A is related to B, then there is no problem. If A is related to B, then B will be related to A. Then by transitivity, this will happen. By transitivity, this will happen. But you can notice that maybe C is here and maybe D is here. So are you getting my point? So you can easily see, look at this relation R. This relation R is, it is symmetric. It is transitive, but not reflexive. Still it is not reflexive. The relation is not reflexive. Why? Because you may not relate to anyone. Yes or no? This may not happen in the first place. Maybe you are isolated. Like for example, like this C. Look at this C. Maybe this C is isolated. So this is not reflexive because C is not related to C. Okay. Now here one very interesting point I want to tell you, and one day I know that some question can be created on this point. Now I am asking something. This is the question. Let's assume relation R on set S. On set S. Let's assume R is symmetric and transitive. Symmetric and transitive. The relation is symmetric and transitive. Consider a element X. This is my question, that if X is related to any element at all, if X relates to some element, if X relates to, this is the question, please read the question what I am saying. R is symmetric and transitive, and there is a X belonging to S. Let's assume there is an element X which belonging to S, which belongs to S, and I am saying that if X relates to some element, at least one element, okay, if X relates to at least one element of S under R, under relation R, then X will definitely relate to X. Then X will definitely relate to X. Is this true or false? Simple question I am asking. See, this is something interesting. Like from the previous question, you can make this statement that you have a relation R on set S. Relation is symmetric and transitive. Now I am saying that there is an element X. Take any element X. If it is related to any element, then definitely it will be related to itself. If it is related to at least one element, then definitely X will be related to itself. Is this true or false? This statement on your screen, is this true or false? Tell me. This statement, is this true or false? So yes, this statement is true, because you can see that if X is related to anyone, like let's consider this is your set X, S, in this you have some elements. Now you can notice if X is related to anyone. See, there are two cases. You know that X relates to someone. You know this. Okay, X relates to someone. This you already know. What are the two cases? You know X relates to someone. Okay, you are defining relation R on S. Now you know this. So there are two cases. What are the case one? Case one is X relates to X. Then there is no problem. Then we are done. Yes or no? In this situation, can I say that we are done already? Okay, in this situation, I can say we are done. Because X relates to someone. X relates to someone. Case one is X relates to X. If X relates to X, then we are done. Okay, we are done. Then X relates to X, we are done. What is the case 2? What will be the case 2? Case 2 will be that X relates to Y, where X is not equal to Y. Okay, where X is not equal to Y. So X relates to Y. Then you can notice that by symmetry, what will happen? Then by symmetry, Y will be related to X. And then by transitivity, X will be related to X. So is this clear? Is the statement clear to everyone? So if you are related to anyone at all, then definitely you are related to yourself. This is the property of symmetric and transitive. So you can see, this is the conclusion you can get, that if you define a relation R on set S, okay, then this property is there. This property is there that if R is symmetric and transitive, then what will happen? Then something interesting will happen, that then if you are either you are not related or you are related to yourself. Okay, can I say? Then for all X, this is what we can say. Okay, see this interesting statement. What I can say? Then I can say for all X, I can say, for all X belonging to S, I can say this will be true. Either X is not related to anyone. Okay, see, either X will be related to X, or this will happen, that for all Y, X is not related to Y. Okay, please tell me, did you understand this? Interesting, right? Yes or no? Once you write in the format of first order logic, this becomes interesting. It becomes a good question for the GATE exam. From the GATE exam point of view, if they give you this, first order logic expression, then this becomes a good question. So we are saying that for all elements, we are saying that either you are related to yourself or you are not related to anyone. Okay, either you are related to yourself or you are not related to anyone. For everyone we are saying, that either you are not related to anyone. See, either you are not related to anyone or you definitely will be related to yourself. So this is the point. I hope this point is clear. So you can see, if relation is symmetric and transitive, if this happens, then what will happen? Then for every x belonging to S, what will happen? Either X is not related to anyone. For everyone this will happen. Either X is not related to anyone or X will be related to X. Okay. Please tell me, did you understand this? Let me know. Did you understand this question? A question. This did you understand? Please tell me. Let me know. So, okay. So very easily you can check it. So I hope this point is clear. So in the GATE exam, they can give you like, there is a relation on set S which is symmetric and transitive, then which statement is true. Then they can give you 4 statements. Okay, some 4 statements they can give you. So you can see, for all elements I can say that either you will be related to yourself or you are not related to anyone. Okay, let's move on. Now let's see the question. This, give an example of symmetric and transitive but not reflexive. This we have seen. This we have seen. So both part A and part B we have seen. Okay. Snooze is asking, it should be exclusive or. It should be exclusive. Yeah, that is also fine. Snooze, that is fine. Okay, this is also correct. Like, this is also correct. Of course, only one of them can happen, right? Yes or no? See, if this happens, then this cannot happen. And if this happens, then this cannot happen. So this is also correct. In the same question, if you put exclusive or, that is also correct. This exclusive or is also correct. Because anyway, one of them can happen. Only one of them. If this happens, then this cannot happen. Okay, if this happens, then this cannot happen. Similarly, if this happens, then this cannot happen. Okay, so you can easily see. So this exclusive or is also correct. Snooze, is this clear? This or is also correct. Like, if you have this or, that is also fine. The statement is true, right? This statement is true. Look at this statement. This expression. This is correct. That you are saying that for everyone, you are saying, for every element, you are saying that either you are related to yourself or you are not related to anyone. Okay, it means that if you are related to someone, then definitely you are also related to yourself. Okay, let's move on. Now let's see the question type 2. So at this point of time, please tell me, are you enjoying this session? All the questions that I have taken, the complete analysis I have done for every question. For each and every question, I have given you detailed, complete analysis. And this is what we do in the Go classes. For every subject, for every concept, okay, in every session, for every GATE question, for every standard question from the standard books, from the standard universities, whatever question we solve. And let me tell you that in the Go classes, we always solve only standard questions, either GATE questions or TIFR questions, NET questions, or I can say standard books questions or standard university questions like NPTEL questions. So I hope you are enjoying this session. Then if you are enjoying this session, please like and comment on this session. Okay. So let's see the next question type 2. Okay, that is equivalence relation questions. Let's see this question. So tell me the answer for this one. This is a question from GATE CSE 2000. A relation is defined on set of integers. So what is the base set? Tell me what is the base set here on the set of integers. So here you can notice this is the base set. The set of integers is the base set. On set of integers, you are defining the relation R. Okay. Now you are saying that one integer is related to another integer if and only if their addition is even. Which of the following statement is true? Okay. So let's see this. So what the question is saying, that you are defining a relation on set of integers. on set of integers you are defining a relation, and you are saying that x is related to y if and only if their addition x plus y is even. Tell me when x plus y can be even? When they have when either both are odd or both are even, right? So this statement basically I can also write like this. This statement I can also say that x is related to y if and only if x comma y have same parity. Have same parity. Yes or no? Can I say? Can I say have the same parity? Same parity means either both odd, both even. Either both odd or both even. Correct? Yes or no? Either both must be odd or both must be even. So because the question is saying x plus y should be even, so addition of two numbers can be even if they have the same parity. Okay, like even plus even is even, odd plus odd is even. So you can easily see that this statement I can say relation R you are defining on Z such that x and y have the same parity. They must be both odd or both even. Okay, so this is the relation that is given to you. Now you can solve this question very easily. So basically now the question is this: x is related to y if and only if x comma y have same parity. Have same parity means either both are odd or both are even. Now you can easily see this will be what? This is going to be reflexive. This definitely will be reflexive because a will be related to a. Either both are odd or both are even. So a will be related to a for all a in the integers. So this is reflexive. What about the next? What about the symmetric? Yes, symmetric also will satisfy because if x comma y, if x is related to y, if they both are odd or both are even, then definitely y is also related to x. If x comma y have same parity, then y comma x also have the same parity. Yes or no? So you can notice if they have the same parity, then y comma x also has the same parity. What about the third? That is transitive property. What about the transitive property? This is also satisfied because if a comma b have same parity, b comma c have same parity. See, okay, this is what I'm saying, that if a comma b have same parity, b comma c have same parity. Like they have same parity. They have same parity and they have same parity. So you can notice a comma b either both are odd, both are even. B comma c both are odd, both are even. So a comma b have same parity, b comma c have same parity, then definitely a comma c will have the same parity. So this transitive relation will be satisfied. See, very simple. You can notice if b is odd, then definitely a comma c will be odd. Okay, so a will be related to c. If b is even, then definitely a comma c will be even. Okay, then this will be satisfied. So whatever you do, you can notice that transitive property is also satisfied. So I can say this relation R, this is equivalence relation, right? Correct? This relation R is equivalence relation. Okay, so definitely this statement is wrong because the relation is equivalence relation. Now the question is asking for equivalence classes. How many equivalence classes are there? Equivalence relation is fine, but how many equivalence classes we have? So once you find the equivalence relation, can you tell me the equivalence class of -10? Can you tell me the equivalence class of -10? This means equivalence class of -10. It means equivalence class of -10. What is the equivalence class of -10? That will be all the elements related to -10, right? Equivalence class of -10. Remember, equivalence class of x. What is that? That is all the elements related to x. That is all the elements that are related to x. Every element that is related to x. This is the equivalence class of x. So this is called equivalence class of x. So what is the equivalence class of -10? All the elements which are related to -10. All the elements that are related to -10. -10 is even. This is even. So it is related to every even number. It will be related to every even number, right? It will be related to every even number. It is going to be related to every even number. So you can notice that this will be set of all even numbers. All even numbers will be in one class. So you can easily see that all even numbers will be in the one class, and similarly all odd numbers will be in the one class. Like for example, if I ask you what the equivalence class of 3, then that will be all the odd numbers. Because 3 is odd number, it will be related to all the odd numbers. Okay, you can notice it will be related to all the odd numbers. This is going to be related to all the odd numbers. So you can notice all odd numbers. So that's it. So everything is covered. So this is equivalence relation, and this has two equivalence classes. There are two equivalence classes. What are those? The equivalence classes are these basically. This is your set of integers. There are two equivalence classes. One is all the even numbers and one is all the odd numbers. So there are two equivalence classes, and this is the partition. Okay, two equivalence classes, and this is the partition of set of integers. One part has all the even numbers, another part has all the odd numbers. So there will be two equivalence classes, and this is the equivalence relation. Answer will be option C. Okay, let's move on. Now let's see this question. Tell me the answer for this one. Your relation is symmetric and transitive. That we have already seen. This is interesting, right? Relation is symmetric and transitive. Then it may not be reflexive. Correct? It may not be reflexive. So the answer will be none of the above. So remember, transitive and symmetric does not imply reflexive. This does not imply reflexive. For example, you can take a base set like 1, 2, 3. Okay, this is your, I can say, base set. Now you can define relation R on A. Relation R you can define like this. Maybe, for example, 1. Okay, like maybe this relation you can take 2, 3. So you can note this is symmetric. This is transitive, but this is not reflexive. This is not reflexive. So this is symmetric, this is transitive, but this is not reflexive. So definitely it may not be reflexive. So the answer is going to be option D. The relation may not be reflexive. Okay, let's move on. Let's see this question. This is GATE 2001 question on relations. So consider the following relations, and the question is asking which of them is equivalence relation. Which of them are equivalence relation? See, equivalence relation you can easily find out. Equivalence relation will have this type of structure. Equivalence relation template. What is that? Equivalence relation general template. Let me tell you about the equivalence relation general template. What is that? Equivalence relation talks about equality, some kind of equality. Okay? Some kind of equality. The equivalence relation, equivalence, as I told you, this equivalence relation talks about some kind of equality. So this is something, this is general, I can say general template, that equivalence relation basically talks about, gives some kind of equality, some kind of, okay, talks about, or I can say gives some kind of equality, some kind of equality, some kind of equality. Equality means sameness. Okay, it talks about some kind of sameness, some kind of sameness. Is this clear? It talks about some kind of sameness, means the general template will be this. If you want the general template, that will be this. The general template will be this, that A is related to B if and only if A, B have same, now something, something, something. This is the general template. Okay, this is the general template, that A is related to B if and only if A, B have same something, something, something. Now this something, something, something you can replace with anyone. Like for example, you can say that have same color. Okay, you can say have same value, means A is equal to B. Or you can say have same remainder when divided by 3. Remainder when divided by 3. Have same remainder when divided by 3. Okay, are you getting my point? So can you see that? So for example, same color, same value means A equal to B, or same remainder when you divide by 3. So all these, if you notice, these are basically the equivalence relations. This, okay, all these. So these are equivalence relations. Same parity, yes, same parity. So you can also say same parity. Okay, so that is also. So you can see that these, all of them are equivalence relation. This is the general template. I am not saying that this. I am not saying that this is how you have to find always. You should take care, but this is the general template. Is this understood to everyone? This template is general template that A related to B if and only if A comma B have some kind of equality. Some kind of equality. Okay. So some kind of sameness they have. Some kind of equality they have. Some kind of equality. So this is what you can use. Now let's solve this question. You can immediately see that. Let's see. A is related to B if and only if A plus B is even. So it means here you are talking about sameness, right? Correct? Basically here what you are saying in this one you are saying that in this R1 you are saying that same parity. A comma B have same parity, right? Correct? I can say A comma B have same parity. Have same parity. So did you get it? Like same parity. They have the same parity. So again some kind of sameness you are talking about. Some kind of, you can notice this, some kind of sameness. Not sameness, this is sameness. Some kind of sameness you are talking about. Okay, so you can notice A comma B have same parity. They must either be both odd or both even. You can notice this is equivalence relation, but this is not equivalence relation, right? This is not equivalence relation. Why? Because it means different parity. A comma B have different parity. A comma B have different parity. So this is definitely, you can check it that this is not equivalence relation. Why this is not equivalence relation? Tell me. What about this R2? This R2 on set of integers, this R2, and you are saying that A is related to B if and only if A plus B is odd. A plus B is odd, that means A comma B have the different parity, right? Okay, it means A comma B have different parity. They have different parity. So this is not even reflexive. First of all, different parity. You can easily see this is not even reflexive. This is symmetric. So this relation R2, you can note this is not reflexive. This is symmetric. This is not transitive. This relation is not transitive. This relation is not transitive because you can notice, for example, 2 related to 3, 3 related to 2. Okay, but you can notice 2 is not related to 2. So you can notice this is not transitive, this is not symmetric. So this is not equivalence relation because you are talking about differentness here. Okay, so definitely this is not equivalence relation. What about this? R3. A dot B is greater than 0 over set of non-zero rational number. Over set of non-zero rational number. So what can I say? What kind of sameness I can say? A dot B is greater than 0. It is 0 over the set of non-zero rational number. You have set of non-zero rational number. When can multiplication be greater than 0? Multiplication is positive, means basically here they are the same sign. Yes or no? Can I say they have the same sign? They have same sign, correct? Agree? Do you agree that I can say they have the same sign? So this is also sameness. R3 is also equivalence relation because this is also talking about sameness. Please tell me, is this clear to everyone? This one. So you can see that they have the sameness. They have the same sign. Okay, A dot B is greater than 0 if they have same sign. So for example, it will be reflexive, it will be symmetric, it will be transitive. Okay, so that is the reason this is equivalence relation. What about this one? R4. A minus B modulo is less than equal to 2. A minus B modulo, okay, the absolute value of A minus B is less than equal to 2. This is not even see, this is reflexive. Yes, this is reflexive. This is reflexive. This is symmetric also, but this is not transitive. This R4, you can check this R4 is not transitive. What this R4 is saying, let's see. Look at this R4. This R4 is on set of natural number. On set of natural number. The R4, the relation is on set of natural number. Now what we are saying? We are saying that R4 is on set of natural number. We are saying A is related to B. A is related to B if and only if absolute value of A minus B is less than equal to 2. So definitely on set of natural number, this is the base set. So you can easily see, yes, this will be reflexive. This relation will be reflexive. This relation will symmetric also. It will be symmetric also because this is the absolute value. This is the absolute value function. This is the absolute value function. So this is reflexive. Why? Because you can notice a minus a, this will be 0 and that is less than equal to 2. This will be symmetric also because this is absolute value function. So the sign actually does not matter. But this is not transitive. The relation is not a transitive. Why this is not transitive? For example, you can notice that there is a see, this 2 is related to 4, 4 is related to 6, but you can notice that 2 is not related to 6. Yes or no? 2 is related to 4. 4 is related to 6, but 2 is not related to 6. So this is not transitive. This relation is not transitive. So this is not a equivalence relation. The answer will be what? Answer will be R1, R3 are equivalence relation. Answer will be option B. The question is asking for correct statement. So the answer is going to be option B. Please tell me, did you understand this? This sameness, did you understand? Let me know. Did you understand this sameness concept? The concept of some kind of sameness you have. Okay, some kind of sameness you have. So this is the general template. The general template, did you understand? For the equivalence relation. Some kind of sameness we are talking about. Okay. Same color, same value, same parity, same remainder when you divide by 3, same remainder when you divide by 4. Okay, same remainder when you divide by k. So something like this, same remainder when you divide by k. So something like this. So this is the concept of equivalence relation, and this is a very beautiful question actually. This is a very nice question. You can easily solve it that R1, R3, they are talking about sameness. Okay, R2 is talking about differentness, and R4 is not transitive. So the answer will be R1, R3 are equivalence relation and the remaining are not equivalence relation. So this is the analysis that we have done. A lot of analysis we have done in this session. Some questions are remaining. Question type 3 is remaining, that is counting the relations. Okay, counting the relations. Counting relations. So this type of questions in which you have to count the number of relations. Count the number of total relation. Total how many relations are possible. How many reflexive relation, how many symmetric, how many anti-symmetric, how many equivalence relation. So this type of questions. Okay. So counting relation, this is the next category of question. Please like the sessions and share with all the GATE aspirants. Okay. These sessions are definitely helpful for all the GATE aspirants because in these sessions we are solving GATE questions with complete analysis. For every GATE questions we are giving you proper and complete analysis. So these sessions are definitely helpful for all the GATE aspirants. Okay. So please share with all the GATE aspirants.